Hello, this is the last theoretical lecture of this course, and it will contain a couple of, let us say, less important notes. The first note will be about bonds. Of course, we would like to simulate more than just liquid argon, that is, small molecules and also large molecules like peptides, proteins, nucleic acids, and so on and so on. Such molecules are flexible, and we have a force field to describe this. These force fields usually contain bonds modeled by harmonic oscillators. Okay, but there are disadvantages of this approach, but also advantages. So let's try the simplest way, that is vibrating bonds. I wrote classical because we are using classical mechanics. It is simple, and we have a consistent model with a simple code to integrate, for example by the Verlet method and so on. We have also flexibility, which we need because molecules are flexible. But the spring that we have, especially if we have hydrogens, are very stiff, and the frequencies are very high. It means that we need very short time steps. In molecular dynamics and in Monte Carlo it's similar. We need very short trial moves, and it's inefficient. Okay, there are methods how to overcome the problem of short time steps in molecular dynamics, multiple time step methods, but it's demanding. Also, the vibrational frequencies we get, especially those which are connected to hydrogens, are very high. They are so high that such a molecule isn't excited even to the first excited state. If you remember, we solved a problem for water, and a water molecule at the boiling point contains less than 1% of molecules which are excited to the first vibrational state. But this vibrational state for water corresponds to bond angles. For bonds, it's even less. So the water molecule is essentially rigid. It's not fully rigid, it's quantum. And that's a question, what is better described by classical mechanics? There have been several works that say that it's better to describe these bonds as rigid than as vibrating, if these bonds are truly described by oscillators which are not excited, I mean. And from the technical point of view, if we have very fast vibrations, and if we had vibrating bonds, then the transfer of energy between these fast vibrations and to the other important, that is slower degrees of freedom, let us say conformational changes, is very slow. We say that these motions are decoupled. Of course, we can overcome it by using stochastic thermostats, but again, these thermostats sometimes are not suitable. And last but not least, these flexible models are quite more difficult to be described theoretically. That is, it may be useful to constrain bonds, or at least some. Monte Carlo simulations of large molecules, whether with fixed bonds or not, are difficult. But what's quite often simulated are small, especially rigid molecules. Here's one example, a linear molecule. It is described by 5 numbers. First, we have a vector, for example, a position of the center of mass. And second, we have 2 angles, which describe the axis. One can expect that a Monte Carlo step would be easy. For example, that we add a random number in certain range symmetrically distributed to one angle, to the theta angle, and to the phi angle we do the same. But this is wrong. And why it's wrong? It's seen on this slice because the element of angle here and here, even if these deltas are the same, these elements don't have the same area, the same space angle. So we have to do it in a different way. This can be fixed, but it's better to do it in a totally different way. For example, if we have a general molecule, like here a water molecule, we can adopt the following algorithm. First, we choose an axis randomly, and this axis can be any of XYZ axes within the body frame, which means one of these three axes, for example, or it may be any of these in the three-dimensional space, it doesn't matter, or it can be any random vector. And then we rotate this molecule around this randomly chosen axis by certain angle, which is symmetric in the same spirit as we know already. And this is reversible, micro-reversible, and it's correct. But let's go back to molecular dynamics with possibly rigid bonds. But it's not so easy. Let's imagine a molecule which has certain bonds which are modeled by harmonic oscillators with certain force constant K. You can write this potential, but it's not important now. There's another atom, again bound by a harmonic oscillator, and let's say another atom here, and perhaps we can consider also this harmonic oscillator or this angle, and so on. We can simulate this. Such a molecule is pretty flexible. And let's now simulate a series of such systems with all force constants increasing, going to infinity. It would be more and more difficult because we would have to use shorter and shorter time steps. But we can imagine this. So one would expect that we'll get, in the limit, a system with fixed, rigid bond lengths and bond angles, perhaps in this case. But this is not true. The dynamics of such a system, even in this limit, is not the same as the dynamics with truly fixed bonds. But still, it's not so bad. For example, hydrogens are typically attached to certain complex molecule at a very specific way. It can be shown that if we fix these lengths of hydrogens, it is the error caused by mechanics is very small. And it is often done because you know that vibrations of hydrogens are very fast, so we gain a possibility to have a longer time step. Okay? We can fix all bonds, but of course we cannot fix too many bonds. For example, it's not a good idea to fix bonds in such complex cases where when we are rings. But we can fix, let us say, bonds on a chain. It's sometimes done too, or aliphatic chains. It's a bit worse, but still acceptable. But other options like angles with hydrogens, it's still well, okay, but it's not used. And of course, it is wrong to fix all bond lengths and all angles. Okay, so we know what to fix. Typically, only bonds with hydrogens is recommended nowadays. We don't have to spare so much, and we have several methods to use. I will speak about them later. And one example with the united atom model of butane. The united atom model means that group CH3 is modeled by one Lennard-Jones sphere, and then there are different energy terms in between here. And I ran several simulations with different flavors of this model, and I draw the dihedral angle distribution. The dihedral angle is the angle between these two planes. Okay, how such a simulation looks like. This is only one molecule. I ran this for dilute gas, actually for many molecules, but you can see here how it looks like where such a molecule has internal rotation. Of course, not all molecules rotate in this way. Some of them just vibrate. This model already has constrained bonds and bond angles. And this is a dihedral angle distribution. With rigid angles and bonds, this is the blue curve, the distribution differs quite a lot from the other two. It's an example of the statement which was shown here. Red and black ones differ too, but a bit only. In this case, angles are flexible, but in one case the bonds are rigid, in the other case the bonds are flexible. But essentially it's not distinguishable. The differences are tiny. So, to have rigid bonds isn't so harmful, but it's quite harmful to make also the angles rigid. Of course, this means for such complex molecules. For water, if we have water molecule and we make the angle rigid, we get a rigid body, and there are no such problems. It's correct. The question now is how to implement the equations of motion with constrained bonds. Let's start with something simple, the mathematical pendulum. The mathematical pendulum is a point with certain mass which is suspended from a fixed point, and this thread has a constant length always. Let's start with the Verlet method. The position of this point at time t plus the time step may be given by the Verlet method in such a way, and you know what the Verlet method is. It is given by this part of the formula. This is the force, the real force acting at time t. But if we take this, we get the position here, and it is not the correct position because the distance is not the same as before. But it gives us a hint how to solve it. We'll add to this real force, which is calculated at time t, this fictitious constraint force at the same time in such a way that this distance is correct. Mathematically speaking, we have this condition. I wrote this condition with this prefactor, but it's not important. Essentially, this constraint force is such that it is an unknown coefficient. You can add this to it. It's not important, but what's important here is this. This is the direction of this constraint force at time t. Why time t? Because we use it already here. That is, this is this direction. And that's it. The rest is just mathematics. The condition of the same length is mathematically given here. A squared position at time t plus h, that is all this, equals this and equals certain L squared if this is L long. We will solve it in such a way that we square both parts, this part with this can be written like this, with the Verli method here used, and this is the original, equal to L squared. The square of this vector is easily calculated using the dot product here, 2 lambda, and a small term here. We can omit here because it's small, then we have to iterate, but we'll see later that we have to iterate for complex models anyway, and if we omit this part, we'll get a very simple formula for the unknown lambda, so essentially for the constraint force. And we insert this back in this way. This is a mathematical pendulum. For atom-atom bonds, we must distribute this lambda, this constraint force, to both atoms, and we distribute it inversely proportional to the masses of particles, because the heavier particle, the less it moves. This is just a straightforward generalization of the idea that I provided for the mathematical pendulum. Don't worry about it. And we'll get also lambda. Okay, to summarize, this method, which is called shake, is based on the Verli method. Because of this, the center of mass is conserved. It should be, because the momentum is the integral of motion. If we have complex molecules, and this is not exact anyway, we have a problem because we have several bonds. So we take them one by one, but if we fix this bond, it may happen that this one gets imprecise, so we must iterate, but usually we need a few iterations if our system is mechanically good, but it must be anyway, otherwise we would have trouble. So if we have fixed bonds with hydrogen, this works fine. There are tricks how to speed up the convergence, and there are versions. You know that there are several versions of the Verli method, like leapfrog or velocity Verli, and here we have also more versions, but of course this is not terribly important. And a few words about optimization. Most potentials that we use in simulations are short range, or we made them short ranged because of truncating them at certain distance. If we simulate quite small systems, it's good enough to have a double loop and check all pairs, whether they interact or not. In moderate size systems, we use usually a trick called a neighbor list. It means that we have somewhere a molecule or an atom, and we have a list of all atoms which are within certain distance, and we only check this list, or check molecules in this list, whether they interact. There must be some extra space around here so that we can use this list for, let us say, several time steps, but then we must update the list. By the update, we include molecules that came from outside and omit molecules that we no longer need, that flew out of this list. And this list exists for every particle in the system. For even larger systems, this is not sufficient. Then we used algorithms which are based on the so-called domain decomposition. One of them is the linked cell list method. In this method, we have a system that contains a lot of molecules like here, and we take a molecule or an atom. We know that we have certain cutoff, so we pre-calculate only those cells that are within this cutoff, and we check only atoms in these cells. There are several versions of this. We can have fixed cells for any atom of the central cell, we have neighbors, or we build up our list of cells from each atom separately, or it can be based on molecules if you have small molecules, and so on and so on. But I hope the principle is known. The linked cell list method is called linked cell because here we need to keep track of a variable number of molecules in a cell, and it is implemented by a trick in programming that is called linked cell list. Essentially, we start by any molecule, like here. We have certain record of this, and here at the end, here are the data, let us say, and here we have a pointer or index number or whatever to another molecule in the list. So here we have another record with data, and so on until until there is the end of the list, which is usually denoted by 0 or null or something like this in the list. A couple of tricks which are sometimes useful. You may find them in the literature. I already spoke about the multiple time-step molecular dynamics. It's useful if you have different time scales like fast vibrations and the rest of the system, or also it's useful for quantum path integral simulations. In Monte Carlo we can do a lot of tricks like multi-moves to move several particles at once. We can have the so-called preferential sampling. In this case, let's have a solute here and smaller molecules around it, and we are interested about what's happening around this solute, let us say a micelle or whatever. So then it's a good idea to sample in Monte Carlo more often molecules that are closer here, but we must do it in a smart way. That is not only to choose more often molecules that are closer, because then microreversibility would be violated, but do it in such a way that it works. No details anymore. In Monte Carlo we can have different special Monte Carlo moves, like identity change of particles. For example, if we have a mixture, we'll get faster change of the configuration. As regards programming tricks, a good programmer must know what the cache is. Now in modern processors we have several levels of cache. Cache is a fast memory that sits close to the processor so that it's fast to exchange data, and good programming means that I know how the cache is fast, how big it is, and I devise the loops in the algorithm in such a way that I need data from the slower parts of memory less often than those that I have already there. That is, for example, instead of one long loop, it's better to split such a loop into several nested chunks and so on. Often it's useful to use splines to calculate the potentials. This is a trick that is useful in many branches of science. If something is given by a complicated formula, it's better to calculate it in a simpler way by a simple formula that is tabulated polynomials. Let us say I have some complex function here, so I split it into chunks, and this part which is short is replaced by a polynomial, usually a cubic polynomial. Nowadays even cheap cell phones contain processors that can run tasks in parallel, and that have several threads. If we have a classical processor, we usually run this in parallel. You can imagine that it is especially easy if we have such a domain decomposition, so we can go through this in layers in parallel. The standard computers now contain from 4 to, let us say, 16 or 32 cores. Usually they have more the so-called threads, so it can be sometimes a bit more efficient. But real large calculations are now done on the graphics processing units. You know these graphics processing units from computer graphics. They are heavily used in computer games. They can render different creatures on the screen very fast, but they can be also used for calculations. This is a challenge because we have thousands of processors, but we don't have enough memory, and usually there are groups of these processors, like 32, that run the same code, but with different data. So it is much more difficult to program. But modern packages that you can download can use the graphics processing units, and the calculations can be in some circumstances by 2 orders of magnitude faster. And the very last page deals with so-called kinetic quantities in molecular dynamics. Kinetic quantities are those where I must use time. I cannot use Monte Carlo or any static calculations. One example is diffusivity. Another example is the electric conductivity, which is a sort of diffusivity of charge, I would say. Viscosity, heat conductivity, and so on. In principle, there are 2 types of algorithms. One is non-equilibrium molecular dynamics. The acronym is NEMD. You should remember this. This is very close to a real experiment. I have a system and I apply a field or a perturbation, and I am looking at what this perturbation does with the system. For example, I can apply an electric field and measure the electric current or current density, and from the ratio of this current density and electric field I get the conductivity. I can apply a thermal gradient and measure the heat conductivity. I can apply shear stress and measure the flow, and I get the viscosity, and so on. If I use this non-equilibrium molecular dynamics, always I get dissipation of energy, because I apply, let us say, electric field. There is an electric current, and there is a joule, it's called joule heat, that is generated. You know it very well from different electric heaters. But from the point of simulations, it means that I need a thermostat, because otherwise the system would heat up. Also, the problem is that if I apply a realistic electric field, I don't calculate anything in a simulation. I must apply a huge field or huge gradient and so on. Then I must extrapolate to zero perturbation. There are several quite smart methods of this type. One to calculate viscosity is here. These are special boundary conditions. Instead of normal boundary conditions like here in the x direction, like cell has a neighbor of the same cell, just shift it. In the y direction, I shift this in a time, so I put certain velocity to all particles here. So when a particle crosses this boundary, I add a velocity in this direction to this particle, and I measure the so-called pressure tensor or stress tensor, and from this I'll get the viscosity. So this is one part of methods that I believe are quite understandable because it's close to the real experiment. The other part of methods is called the equilibrium molecular dynamics. It's the normal molecular dynamics without anything added, without any perturbation added. So there is no heat generated, but I need smart formulas how to calculate what I want. That is, in principle, I run one simulation and I can get many quantities out of it. What I need is a theory. This theory is called the linear response theory. It is based on the idea that I add a very small perturbation here, a virtual one, and then I sit down and calculate and get a theoretical formula from this infinitesimally small perturbation. And such one example of such a formula here, just an example, you don't have to memorize it, of course. Thus, the diffusivity can be calculated from the correlation between the velocity of a particle at time t and its velocity at time 0. And this correlation is integrated over time. There are more complicated formulas for viscosity, for electric conductivity, and so on. Another formula which actually is equivalent to this formula is here. I believe you do know this formula from physical chemistry or from physics. It tells us that the mean square displacement of a particle during the Brownian motion, every particle moves chaotically from point to point, is proportional to time, and it is the diffusivity here. I will show you how diffusivity behaves. This is one particle that travels through space, and after some time it gets from one point to the other point. And let's do this pseudo experiment many times and make statistics of it. And the statistics looks like this. So this is, let us say, perhaps 1000 times, and I get different points here. So I must do statistics, and in fact the formula which is below tells me that the size of this cloud of points, how the particle traveled within time, is connected to the diffusivity. So this is the principle. Here you can see the diffusivity in a real experiment, or real experiment. No, if I almost real experiment, simulated real experiment, if I put a dye into the system, it diffuses. I'll skip this. Okay, I guess this is also what I wanted to tell you as regards the theory, and what's left for us is essentially some more pseudo experiments shown, and one pseudo experiment for you to do by yourself. Thank you for your attention.